In the previous video, I explained the concept of resonance in an LCL filter, discussed its impact on inverter performance, and explored both active and passive methods for effectively damping these resonances. In today's video, I'll demonstrate how to simulate a three-phase grid-connected inverter using synchronous reference frame control in Matlab. I'll also show how to provoke resonance in the simulation and then mitigate it using a passive circuit. So let's get started. Now I'll provide you with the LCL filter values used in the simulation. I won't go over the design of the LCL filter here because I've already covered that in one of my previous videos. The inverter side inductance value is 3.6 mH, the grid side inductance is 1 mH, and the capacitance is 4.7 microfarads. We can calculate the resonant frequency of the filter from these values using the equation, the square root of L1 plus L2 divided by L1 L2C. After substituting the values, we find the resonant frequency to be 2624.37 Hz. I'll use this value during the simulation. Now, I'll demonstrate how to design a damping circuit. I'm employing a straightforward resistor-based damping circuit, where a resistor is connected in series with the filter capacitor. The damping resistor value is calculated using the equation, Rd equal to 1 by C into 2 pi into FSW, where FSW is the switching frequency. Upon substitution, we obtain Rd equal to 3.3 ohms. I'll utilize this value during the simulation. This is the block diagram for synchronous reference frame control used in the simulation. I covered the controller's details in one of my previous videos, so you can refer to that for a deeper understanding. Now, let's open Matlab and begin the simulation. Add an IGBT. Create three-phase H bridge using IGBTs. Uncheck this box. Add an IN port. Name it as PWM1. Connect the port to the gate terminal of all the IGBTs. Add a connection port. Name it as VDC+. Copy the port. Name it as VDC-. Connect the ports to the positive and negative ends of the H bridge. Copy the port. Name it as VR. Keep the port location right. Copy the port. Name it as VY. Keep the port location right. Copy the port. Name it as VB. Keep the port location right. Create a subsystem from the selection. Delete all the signals. Add a DC voltage source. Connect it to the H bridge. Set the voltage 800. Add a from block. Name it as PWM1. Connect it to the subsystem block, and similarly add other PWM signals also. Name it as PWM2. Name it as PWM3. Name it as PWM4. Name it as PWM5. Name it as PWM6. Add a current measurement block. Connect to all the three phases. Add a go-to block. Connect to the measurement block. Name it as IR. Name it as IY. Name it as IB. Add a series RLC branch. Set branch type, L, and value 3.6 mH. Connect it in all the three phases. Copy the RLC branch. Set the branch type, RC, resistance 0.002, capacitance 4.7 microfarad. Connect it in all the three phases. Copy the RLC branch. Add a three-phase I measurement block. Set the parameters. Connect to each inductor. Add a demux. Set the number of outputs 3. Add a go-to block. Name it as VR. Name it as VY. Name it as VB. Add a three-phase voltage source. Flip the block left-right. Connect to the measurement block. Set voltage 400, phase angle 0, frequency 50, source inductance and resistance very small values, and base voltage also 400. Now drag and drop the voltage signals. Add a mux. Set number of inputs 3. Add AABC to alpha beta block. Add a alpha beta to DQ block. Add a go to block. Name it as alpha beta. Add a from block. Name it as omega t. Add a demux. Set the number of outputs 3. Add a go to block. Copy the go to block. Name it as VD. And name it as VQ. Copy the entire block. Delete the alpha beta signal, and change input signals from VR, VY, VB, to IR, IY, and IB. And change output signals from VD, VQ to ID and IQ. Add a alpha beta to DQ block. Connect alpha beta signal to the input. Add a demux. Set number of outputs 3. Add a sum block. Connect to the second output of demux. Change its sign to plus minus. Add a constant block. Set the value 0. Add API controller. Make controller type PI, and set the values of KP and KI. Add an integrator. Add the output of integrator to the omega t signal point of the transformation block. Add a go to block. Name it as omega t. I forgot to change the value of these inductors. Set all the 3 inductor value, 1 mH. Add a constant block. Set the value -40. And that is the reference value of the grid current. Add a sum block. Change its sign to plus minus. Drag and drop the ID signal.
Add APID controller.
Make controller type PI, and set the values of KP and KI. Add another sum block.
Add a gain block.
Set the gain value, 2 into pi into 50 into 4.6 a power minus 3. Now drag and drop the IQ signal.
Copy the sum block.
Now drag and drop the VD signal.
Add a goto block.
Name the signal ED. Add another constant block. Set the value 0.
Copy the sum block.
Connect IQ signal to sum block.
Copy the PID controller. Copy the sum block. Copy the gain block.
Connect ID signal to gain block.
Copy the sum block.
Connect VQ signal to sum block.
Copy the goto block.
Name it as EQ. Drag and drop ED and EQ signals. Add a mux. Set number of inputs 3. Add ADQ to ABC transformation block. Connect omega T signal to the block.
Add a demux.
Set number of outputs 3.
Add a gain block.
Set the value 2 by 800.
Copy the gain block. Add a relational operator. Change the operation to greater than or equal to. Add a repeating sequence.
Set the time and output values for 10 kHz, -1 to 1, triangular carrier signal. Connect this block to relational operator.
Add a logical operator.
Set the operation NOT. Connect this block to relational operator. Now connect all the outputs to the PWM signals of the IGBT. Now copy all the voltage and current signals.
Add a scope.
Change the scope settings. Connect voltage and current to the scope.
Add a power guide block. Set simulation type discrete and sampling time 1e raised to -6. Open the model settings.
Choose fixed step solver type. And step size 1e power -6.
Set simulation time 1 second and run the simulation.
Open the scope to view the grid voltage and current. This is the voltage and current, and the grid current amplitude is same as the reference value. So the controller working fine. Now we will see how to excite the resonance in the inverter. To do that, we need to inject a voltage of a certain magnitude with a frequency same as the resonance frequency of the LCL filter. First I will copy the three-phase source. Connect this source in parallel with the existing source. Set the voltage 20, frequency 2624.37 Hz, which is same as the resonant frequency of the filter.
Now run the simulation again.
Open the scope to view the grid voltage and current. Here you can see that, after introducing the resonance, the grid current looks highly distorted with lots of high-frequency component present in it. This shows the challenge posed by resonance in grid-connected inverters. To address this issue, it's necessary to incorporate damping into the system. In this simulation, I'll demonstrate a passive method for dampening grid current oscillations. To achieve this, we'll include a series resistance alongside the filter capacitors. The designed resistance value is 3.3 ohms, which I'll now add into the circuit. So change the value to 3.3.
Now run the simulation again.
Open the scope to view the grid voltage and current. Now you can clearly see that after introducing the damping, the distortion in the current has disappeared, and this is how we use the passive method of the damping in the grid-connected system. So in this video, I demonstrated how to simulate a 3-phase grid-connected system with SRF control, how to excite the system with resonance, and how to mitigate the resonance with a damping circuit. I hope you understood the concept. This is the end of this presentation. Thanks for watching.